Based on spectroscopic observations, the 10 most common elements in the Milky Way include hydrogen, helium, oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, and sulfur. This indicates that the Milky Way has a long history of formation, consisting mainly of celestial bodies of small to medium sizes. According to physics theory, stars of this type typically have lifespans ranging from several billion to up to 10 billion years. The abundance of oxygen, carbon, and iron serves as the clearest evidence that many of these stars have exploded, corresponding to events like novae or type Ia supernovae. Larger supernova events certainly occur, but they are far less frequent. Today, the Sun is believed to be a second-generation star in the Milky Way, meaning it formed from the nebulae of a previous generation of stars that exploded. These nebulae contained many heavy metal elements, with Earth being a prime example. Our planet is composed of a wide variety of complex components, the most common of which include oxygen, silicon, aluminum, iron, calcium, sodium, magnesium, potassium, titanium, and finally hydrogen. Of course, this ranking is based on mass percentage, not the number of atomic particles. In addition to these common elements, Earth also contains many heavy metals, such as gold, platinum, lead, and uranium, among others. This suggests that the protosun's predecessor must have been a very massive star, as only a supermassive star could have had the energy to fuse elements heavier than iron through its supernova explosion. According to physicists, such massive stars are typically primordial stars from the first generation of the universe. They were formed from very pure materials and had short lifespans. So, what exactly is a primordial star, and do they still exist today? The answer is certainly no. To differentiate, primordial stars have two main characteristics. First, the elements that make up a primordial star must be entirely pure, untainted by any other elements except hydrogen and helium. Second, they are extremely massive, potentially 1,000 to 10,000 times larger than the Sun. In astrophysics, primordial stars are a rather fascinating topic. These stars exist only in theory. No one has ever actually observed them. This is because primordial stars had very short lifespans, appearing shortly after the Big Bang and not surviving to the present day. On the other hand, the dust clouds and nebulae in the current universe have lost their purity, having been mixed with many metallic elements. Although these elements make up only a tiny fraction, they greatly influence the formation of new stars and even the process of life formation. The truth is, a primordial and pure universe is one that cannot form life. Fairly speaking, every star or planet in the universe today can be considered a partially primordial celestial body. The same applies to you and me. We are all made from both primordial and non-primordial components. Overall, we are much older than we might think. Keep in mind that up to 98% of the matter in the universe today consists of primordial components formed right after the Big Bang. Since then, no new components have been created. This means that since space began to cool, the universe has stopped producing new hydrogen and helium. Theoretically, remember, this is just theoretically, hydrogen can still be created through high-energy events, even in particle accelerators. However, essentially all the hydrogen and helium in the universe today are primordial elements, formed right after the Big Bang. For instance, our Sun is composed of 98% hydrogen and helium, about 1.5% carbon, nitrogen, and oxygen, with the remaining elements being neon, magnesium, silicon, sulfur, and iron. This means that about 2% of the Sun is made up of heavy elements, which are not primordial. The other 98% are entirely primordial components. This also means that even the hydrogen in our bodies is an incredibly primordial element, as old as the universe itself. However, it's important to reiterate that if the universe remained so primordial and pure, life would not have been able to form. When looking at Earth from space, we see that the planet's surface consists of two main elements: oceans and continents. Chemically speaking, oxygen and silicon are two extremely common elements. Almost everything around us contains oxygen, from air to water, rocks, and even metals. The second most common element is silicon, also known as silicium, which is the primary component of sand and rocks. However, there is another element that is incredibly abundant on Earth, and which we believe is absent from almost all other known planets: life. Life is extremely diverse and abundant, to the point that we don't even know all its forms. In fact, 99% of life on this planet is unknown to humans, mostly consisting of microorganisms and many species that have been wiped out throughout Earth's history. The truth is, we still don't know when or how life began, but there is one thing we do know: life is governed by a chain of DNA molecules. DNA stores genetic information and controls the process of protein synthesis. In a way, DNA is like the blueprint of life, and it is made up of a chain of carbon molecules. Of course, it's not entirely carbon. It also includes oxygen, nitrogen, and hydrogen. But carbon is the main component, and carbon is not a primordial element. Carbon is only created within stars and is released into space when stars explode. This means that it was only after the first generation of stars in the universe exploded that the components necessary for life began to emerge. As we can see, even the simplest form of life is made up of non-primordial elements like carbon, oxygen, and nitrogen. The more complex life becomes, the more chemically diverse it becomes. For example, the human body consists of 65% oxygen, 18% carbon, nearly 10% hydrogen, 3% nitrogen, 1.5% calcium, and about 0.6% phosphorus. The rest includes potassium, sodium, chlorine, magnesium, copper, zinc, iron, selenium, and several other heavy metals. Note that these components are measured by body mass percentage and can vary from person to person. However, in general, we are made up of many elements, which represent only a small fraction of the periodic table, covering both light and heavy elements. Except for hydrogen, all the other elements are products of supernovae. It's not an exaggeration to say that stars are our creators. We just don't yet understand exactly how the process of shaping us took place. Looking at the material composition of the Milky Way, we see that the elements necessary for life are currently in abundance. Clearly, this period is a golden age for the formation of life. This is likely the case for other galaxies in the universe as well. Theoretically, life could have formed shortly after the first generation of primordial stars exploded. However, in terms of conditions, the universe's first billion years were very chaotic, with extreme events happening constantly. As a result, the likelihood of life forming during that time was low. When the universe reached about 5 billion years of age, large and medium-sized stars had already burned out. They released many of the elements necessary for life, and it was during a similar event that our solar system began to form. Jupiter, the giant of the solar system. When we think of Jupiter, the first thing that comes to mind is its enormous size. Jupiter is a prime example of a supergiant gas planet, a type that is extremely common in the universe. This kind of planet is composed primarily of primordial elements. Nearly 100% of Jupiter is made up of hydrogen and helium, with about 90% hydrogen and roughly 10% helium, while all other elements can only be measured in parts per thousand or million. This gives Jupiter a structure quite similar to a small star, but it lacks the mass needed to initiate nuclear fusion and become a true star. Since Jupiter is made of gas, it doesn't have a solid surface like rocky planets do. Imagine if you were to parachute down to Jupiter, you wouldn't be able to land safely. The deeper you go into the planet, the denser its atmosphere becomes, and the pressure gradually increases until you get stuck in a thick layer of gas. You wouldn't be able to fall any further, nor could you return. It's similar to being trapped in a layer of mud, and you would only stop descending once your body's density matches that of the surrounding gas layer. Even if you had a spaceship, you couldn't safely fly through Jupiter's atmosphere. Besides the super powerful winds and flows, the atmospheric pressure is extremely harsh. It would quickly drag your spacecraft down, and the deeper you go, the faster the temperature rises. Eventually, the spacecraft would be crushed and melted. In terms of basic physical properties, Jupiter has a diameter 11 times larger than Earth, about 139,820 kilometers. Its mass is 318 times greater than Earth's, and its volume is 1,300 times that of Earth, meaning you could fit 1,300 Earths inside if Jupiter were a hollow planet. Jupiter rotates on its axis in just 9 hours and 55 minutes, making a day on this planet 2.4 times faster than on Earth. In terms of size, Jupiter generates an incredibly massive gravitational force. Its surface gravity is 2.5 times greater than that of Earth. If a person weighs 70 kilograms on Earth, they would weigh 175 kilograms on Jupiter. This brings up an issue. Earlier, I mentioned that Jupiter doesn't have a solid surface to stand on. So how is its surface gravity calculated? In fact, Jupiter's atmosphere experiences a wide range of pressure levels as you move inward toward the planet. To make a reasonable comparison, scientists calculate its surface gravity at the point where the pressure is roughly equivalent to Earth's. Thus, the surface gravity of Jupiter, being 2.5 times stronger than Earth's, is measured at the depth in its atmosphere where the pressure is about 1 bar. This occurs at around 10 to 20 kilometers from the planet's upper atmosphere inward. Since 1973, 8 spacecraft have flown by and captured images of Jupiter. Besides Earth, only Mars and Jupiter currently have spacecraft orbiting them. This highlights the importance of exploring outer planets, especially the growing need to search for life and potential new habitats for humanity in the future. From a distance, Jupiter looks like a colorful tapestry with diverse patterns. However, as you get closer, the planet reveals its deadly nature. Currently, the Juno spacecraft is studying and collecting data about Jupiter and its moons, operating at a distance of just 4,200 to 8,000 kilometers from the top of Jupiter's clouds. This is an extremely close range, comparable to the distance between the International Space Station and Earth's surface. At this altitude, Juno faces significant dangers and must accelerate to about 240,000 kilometers per hour as it approaches the planet. Essentially, Jupiter is incredibly massive and intimidating. Its thick, turbulent cloud layers swirl violently at speeds over 600 kilometers per hour, mixed with numerous lightning storms and cyclones. Scientists today still don't fully understand why there are opposing currents crossing the planet. Besides the turbulence and temperature differences between the cloud layers, there are likely other unknown factors at play. This type of weather is characteristic of gas giants, marked by extreme and unsettling conditions. Along with its terrifying weather, Jupiter also produces significant radiation. Interestingly, the source of this radiation comes not only from the planet itself, but also from external factors. It's no surprise that the giant of the solar system has the strongest magnetic field of all the planets. This magnetic field is believed to originate from the flow of electrically charged particles within its core, combined with its rapid rotation. This combination creates a planetary magnetic moment 18,000 times stronger than Earth's. Any charged particles in the space surrounding Jupiter are influenced by this magnetic field, including negatively charged electrons, positively charged cations, and even heavy ionized atoms like oxygen and sulfur. Some of these particles originate from Jupiter's atmosphere, but the majority come from its moon Io. Due to Io's intense geological and volcanic activity, it continuously ejects tons of sulfur dioxide into space every second. This material is immediately broken down and ionized by Jupiter's magnetic field. Thus, these particles, initially just gas, dust, and water vapor, are accelerated by Jupiter's magnetic field to extremely high speeds, becoming highly dangerous particle streams. They constantly bombard and damage the electronics on spacecraft. According to measurements from the Juno spacecraft, the high-energy radiation particles in Jupiter's magnetic field are about 10 million times stronger than the radiation from an X-ray scan, in addition to possessing a vast magnetosphere that extends all the way to Saturn's orbit. Jupiter also exerts its powerful influence by maintaining the stability of the asteroid belt. The asteroid belt is essentially a ring of meteoroids made up of millions of objects, ranging from ice and rock to metal. This stability is a crucial factor in maintaining the peaceful environment for the inner planets, including Earth. Of course, maintaining the asteroid belt's orbit is just part of the story. In reality, Jupiter is also continuously gathering mass from this belt. According to some reports, the rate at which meteoroids fall into Jupiter is about 8,000 times higher than on Earth. This includes many large meteoroids, and even comets weighing billions of kilograms. So, the question arises, if Jupiter is constantly accumulating more material, is it growing? Is it getting heavier over time? The answer is that all of this is negligible. Besides accumulating material, Jupiter also loses mass in various ways. It has a warm atmosphere, and the high temperatures cause gas molecules to move fast and chaotically, to the point that some are occasionally ejected into space. Moreover, the solar winds cause Jupiter's atmosphere to become ionized. These ionized atoms are easily expelled into space by its strong magnetic field. Light atoms like hydrogen, once ionized, behave like simple particles and are easily carried away by magnetic fields and thrown into space. As a result, Jupiter is actually losing more mass than it is gaining from incoming material. Although this process is slow and negligible, Jupiter is indeed gradually losing mass over time. Its massive size indicates that it was one of the earliest planets to form in the solar system. But despite its best efforts, Jupiter cannot become a star, not even a brown dwarf. According to scientists, the mass threshold for any celestial body to be classified as a brown dwarf ranges from 13 to 80 times the mass of Jupiter. This means Jupiter would need to merge with at least 13 planets of similar mass to become a true brown dwarf. At 13 times Jupiter's mass, the core of the body would be hot enough to burn deuterium, a rare isotope of hydrogen. Though deuterium makes up only a tiny fraction of the universe, around 0.00156%, it can start nuclear fusion reactions at a lower temperature than hydrogen. Specifically, when the core temperature of a celestial body reaches around 10 million Kelvin, deuterium fusion begins. Deuterium is essentially composed of one proton and one neutron, and it will fuse with another hydrogen atom to produce helium-3. When the mass of a celestial body increases to about 60 times that of Jupiter, it can fuse tritium, also known as hydrogen-3. Tritium consists of one proton and two neutrons, with a half-life of about 12 years. After undergoing beta decay, tritium decays into helium-3, releasing a substantial amount of energy in the process. When the mass of a celestial body reaches 75 or 80 times that of Jupiter, it begins to be classified as a red dwarf, a true star in the main sequence. At this point, the star has the full capability to burn hydrogen and helium. Thus, we can see that a brown dwarf is a celestial body with properties and characteristics that lie between the concepts of a star and a planet. A brown dwarf can fuse deuterium to produce energy. Although deuterium is not as abundant as hydrogen, it has a lower reaction temperature. In general, nuclear fusion processes in the core of a brown dwarf occur sporadically, and after these reactions end, the brown dwarf does not collapse or evolve into another type of celestial object. Essentially, a brown dwarf will always remain a stable celestial body, as long as its mass is less than 75 or 80 times that of Jupiter. Currently, Jupiter is the largest and heaviest planet in the solar system. Its mass is 2.5 times greater than that of all the other planets combined. This means that even if Jupiter could somehow swallow all the other planets in the solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, its mass would only increase by about 30%. The truth is, there is no way for Jupiter to accumulate enough mass to become a star, even a modest one. Jupiter will always remain a gas giant, and this will not change until its outer layers are blown away by the sun. This is a scenario that will happen, or is likely to happen, when the sun enters its red giant phase at the end of its life. Like many other stars in the universe, the sun is a G-type star in the main sequence. G-type stars are neither too small nor too large, and their lifespans generally hover around 10 billion years. This means that in about 5 billion years, the sun will burn through all its hydrogen and helium. Then it will begin to expand, growing to encompass the orbits of Earth or even Mars. Although many people may not want to imagine such a grim scenario, most scientists today agree that Earth will ultimately be engulfed by the sun's outer layers at some point. Even Mars, despite its more distant orbit, may face a similar fate as Earth. But what about the gas giants beyond Jupiter? What will happen to them? The answer to all of this lies with the sun. The red giant phase of a star like the sun won't last long. As the sun expands, its temperature will drop, but the amount of radiation it emits will increase significantly. Essentially, this increased radiation results from two factors. First, the sun's core begins to heat up, and second, the surface area emitting radiation expands. Astronomers have observed several exoplanets in the universe under similar circumstances. They call these planets hot Jupiters, as they orbit stars that are evolving into red giants. In some cases, these planets lose mass rapidly due to stellar winds. However, in other cases, the opposite happens. The planets don't erode and may even expand as they absorb vast amounts of radiation and material particles emitted by their host stars. However, the real turning point has yet to begin. Everything will truly change when the red giant star reaches the planetary nebula phase, shedding its outer layers and collapsing into a white dwarf. At this stage, gas giants like Jupiter or Saturn will likely struggle to retain their atmospheres. It's highly probable that Jupiter and Saturn will lose part of, or even their entire atmospheres, leaving behind only their cores. As for planets like Uranus and Neptune, they will be less affected due to their relatively distant orbits. Of course, this is a speculative scenario, but it is grounded in logical reasoning. The process may not unfold exactly as described, but the ultimate outcome is difficult to avoid. This leads to an intriguing question. If Jupiter and Saturn are reduced to just their cores, what will they look like? And what exactly are their cores made of? The truth is, scientists aren't entirely sure what the cores of gas giants like Jupiter or Saturn consist of. These planets are immense gas giants with thick, turbulent atmospheres, making it difficult to explore their internal structure, particularly their cores. However, by applying the principles of physics and measuring key factors such as radiation and magnetic fields, scientists can make some educated guesses. Since Jupiter is primarily made up of hydrogen and helium, its internal structure likely changes as you move inward, depending on the state of these elements under varying pressures and temperatures. Beneath the outer layers, there would be liquid hydrogen. Going deeper, there would be liquid metallic hydrogen. This occurs because, under extreme pressure and temperature, hydrogen transitions from a simple gas to a liquid, and eventually becomes metallic. In the periodic table, most elements fall into three main categories: gases, metals, and nonmetals. Hydrogen is naturally a gas, but when compressed under high pressure, it becomes a liquid gas, and when compressed even further, it turns into liquid metal. Of course, Jupiter's temperature is not hot enough to fuse hydrogen into other elements. It can only compress hydrogen to change its state. And the most extreme state Jupiter can induce is turning hydrogen into a form of matter with metallic properties. Conceptually, liquid metallic hydrogen is a state where electrons are squeezed out of their atoms, allowing the hydrogen to conduct electricity like a metal, meaning the electrons can move freely through the substance, similar to how electric currents flow. When this combines with the planet's rotation, the layer of liquid metallic hydrogen acts like a dynamo, generating Jupiter's strong magnetic field. As for the planet's innermost core, it is likely composed of hard rock and metal. However, this core is not exactly like the rocky planets we are familiar with. Measurements of Jupiter's gravitational field taken by the Juno spacecraft reveal that its core is much larger than previously predicted, and, interestingly, it appears less solid than expected. This means the composition of Jupiter's core remains a complete mystery. The latest technical data suggests that the core is large and somewhat diffuse, but it is still possible that a smaller, solid core exists within. In summary, the cores of Jupiter and Saturn remain one of the great mysteries of gas giants. Hello everyone. When a photon is born, it immediately embarks on its journey to its inevitable end. In the context of Einstein's four-dimensional spacetime, the photon leads the dullest life in the universe. Its entire existence consists of just two moments: its birth and its collision with something. Traveling at such a high speed, the photon experiences neither time nor space. In the eyes of a photon, the universe consists of only a single dimension: no length, no width, no height, no depth, and not even movement. But is the photon truly a stable particle, capable of existing forever? To some extent, based on our current understanding, photons are essentially stable particles. If they weren't, the universe would be incredibly dark, and light from distant galaxies would never reach Earth. The stability of photons is fundamental to our understanding of the universe. However, whether they can exist forever is still an unresolved question. In nuclear physics, photons, electrons, and gluons are considered fundamental and stable particles. This means that under normal conditions, without interacting with anything, and with infinite time passing, these particles would continue to exist without decaying. Then there's the proton. Humans have never observed a proton spontaneously decaying, and its lifespan is nearly eternal, estimated to be around 10 to the power of 30 to 10 to the power of 36 years. In fact, many physicists believe that the proton is an eternally stable particle, just like the photon, electron, and gluon. Overall, the stability of protons is a good thing, because if protons were to decay, it could lead to the collapse of all matter. For life, that wouldn't be very enjoyable. So, in terms of physics, photons do not decay into other particles. However, there are some strange effects related to photons that we cannot ignore, such as pair production, transformation, or photon splitting. For example, a high-energy photon can interact with another high-energy photon to create a pair of particles and antiparticles. A high-energy photon can also interact with an electron, losing most of its energy and becoming a lower-energy photon. Photon splitting can also occur in non-linear magnetic environments, where the original photon transforms into multiple lower-energy photons. This is a special case that only happens under extreme conditions. Remember, under normal conditions or in the vacuum of space, photons never split. Additionally, photons can also transform into hadrons, nucleons, with actual mass. I mentioned this process in a previous video, and it is called energy-to-mass conversion. In terms of charge, the photon is a neutral particle, meaning it doesn't violate the law of charge conservation, and thus it will not decay into charged particles. In summary, photons are certainly stable particles, but how long they remain stable is still unknown. What we do know is that photons can lose energy over time, which contributes to the heat death of the universe. This is clearly a long and complex story that requires much analysis. First, let's understand what heat death is. Heat death is a predicted outcome for the universe's distant future based on the logic of space expansion and its consequences. Since the 1920s, evidence of space expansion was confirmed by the astronomer Edwin Hubble. As the universe expands, all galaxies move away from us, a phenomenon observed as redshift. This is where the core of the issue lies. We know that the speed of a photon in space is constant. However, as the distance between its source and its destination increases, the photon gradually becomes tired. Remember, a photon's speed never changes, but its energy does. The energy of a photon is tied to its frequency. The higher the frequency, the more energy it has. As the distance between the source and destination increases, the photon loses energy along its journey, meaning its frequency decreases as the distance grows. Of course, too much of anything isn't good. If the universe keeps expanding and the distances between galaxies keep increasing, the frequency of photons will continue to decrease. Essentially, photons carry energy, but that energy is not infinite. Eventually, if energy continues to decline, there will come a day when it reaches zero. That will be the moment the universe ends, ending in cold and darkness. Imagine that when the last star in the universe burns out, the only remaining light consists of photons drifting aimlessly through space. Over time, even these photons weaken, to the point where they can no longer interact with any form of matter, because their energy is approaching zero. Once photons no longer interact, we will have no way to detect them. If humanity were still around at that time, we would witness the universe becoming truly invisible, while the temperature of space would approach absolute zero. In principle, a universe that cannot be observed is one that is entirely dark and cold. So, what would happen if the universe's temperature approached absolute zero? In the field of physics, particularly in studies of Bose-Einstein condensation, temperatures approaching absolute zero cause atoms to clump together, and the energy levels of the atoms drop to a minimum, making their movement extremely slow. Hypothetically, just hypothetically, if the temperature were to reach absolute zero, all photons would begin to escape from atoms, causing electrons to fall to lower energy levels, eventually collapsing into the nucleus. All atomic activity would cease, electromagnetic forces would weaken drastically, and the fundamental laws of physics, as we know them, would gradually lose their validity. However, one thing is certain: this will never happen. The universe will never reach absolute zero, because there are fundamental principles and barriers that prevent it. Even atoms themselves can never become completely motionless. The first barrier is Heisenberg's uncertainty principle. This principle states that it is impossible to simultaneously measure both the precise position and the momentum of a particle. If you know the exact position of a particle, you will have no knowledge of its momentum, and vice versa. The second is the Pauli exclusion principle. Two fermions cannot occupy the same quantum state in the same system. For example, two electrons cannot share the same energy level within an atom. If the temperature approaches absolute zero, the electrons in an atom reach extremely low energy states, but they cannot overlap. Each electron must maintain a specific energy level, determined by its position relative to other electrons. This ensures that interactions between particles in an atom are always maintained and cannot be completely shut down. The third factor is quantum fluctuations, which cannot be eliminated. These fluctuations act like a background energy for particles. When the temperature drops to extremely low levels, this background energy keeps atoms active and prevents the temperature from ever reaching absolute zero. The fourth is the Bose-Einstein state. Near absolute zero, matter begins to condense, and bosons tend to merge or behave uniformly. Unlike fermions, bosons are not restricted by the Pauli exclusion principle and can occupy the same quantum state as other particles. Experimental studies of Bose-Einstein condensates show that bosons tend to coalesce into a shared state. This results in atoms oscillating in unison, as if they are part of a single, unified entity. And finally, an equally important factor is spin. Theoretically, a particle's spin can be altered, but it can never be stopped. A particle is born with spin, and it cannot cease spinning. We don't fully understand why all particles possess spin, but we do know that they never stop. In a sense, spin acts like a particle's perpetual engine, generating what is known as a magnetic moment. the magnetic moment, is the result of the combination of a particle's spin and its electric charge, and it is observed through its interaction with magnetic fields. When a particle with a magnetic moment moves through a magnetic field, its trajectory can be deflected, or its spin can even change. While the magnetic moment is a form of motion, it is not considered a force, because it only takes effect when interacting with a magnetic environment. In all other cases, the magnetic moment doesn't affect the particle's motion. From these concepts, we can conclude that a photon does not have a magnetic moment since it carries no electric charge. While electric charge doesn't always determine whether a particle has a magnetic moment, it's certain that photons are not influenced by magnetic fields. Each particle is born with its own distinct intrinsic properties, such as mass, charge, spin, and quantum interactions. These properties are completely natural, a wild aspect of the universe's fundamental design. For photons, they are born without mass, charge, or magnetic moment. This gives photons a very unique set of characteristics. Photons are almost unaffected by natural laws, in the same way that particles with mass are. In the double-slit quantum experiment, a photon can interfere with itself. Furthermore, photons do not experience time or distance. It's as if photons exist everywhere in the universe, capable of being anywhere, seemingly unaffected by time or location. This is part of the photon's unique identity, a mystery embedded in the workings of the quantum world that we have yet to fully understand. Compared to all particles with mass, the photon seems like a wild force of the universe, immune to most physical laws, including time. Cosmological models cannot predict where photons will end up in the end, nor how new photons will be created if the universe ends in heat death. If the universe continues to expand, the density of photons will decrease as space enlarges. In our measurements, photons gradually lose energy through the Doppler effect. So, where does the photon's lost energy go, and what will happen to photons if they lose all their energy? Is it possible that the energy is transferred into space through the mechanism of expansion? The answer is certainly no. The total energy of the universe remains constant, but the volume of the universe grows larger. However, even if the distance between objects stretches to hundreds of billions of light years, the frequency of photons remains the same if the source and destination don't change. This provides the solution to the question, where does the photon's energy go as it moves through an expanding universe? It can be said that the photon doesn't actually lose energy. Rather, we ourselves are moving relative to the cosmic microwave background and the photon's source. This concept is called a reference frame. Often, we forget that Earth is a moving planet. We observe and measure the universe from a moving reference frame. In reality, a moving reference frame always involves changes in time and velocity, which leads to the perceived changes in the photon's energy over time, depending on the measurements taken. Therefore, the redshift of photons is due to the expansion of space, and the fact that our reference frame is not stationary, rather than a change in the photon itself. The photon's energy remains constant, but when time and velocity are factored in, its initial energy appears to change. This is all because we exist in a non-static universe, causing our measurements to evolve over time. Pay attention to the fact that redshift measurements always include an important parameter, the expansion factor. The expansion factor is directly proportional to the fatigue of the photon, and it changes over time. No matter where you are in the universe, your reference frame is always shifting. Essentially, a fixed reference frame does not exist within an expanding universe. Many people, including myself at one point, have thought that the volume of space increases while the total energy remains unchanged, much like an irreversible dilution. In other words, the photon density decreases per unit of space. This leads to the idea that the photon's energy is gradually being absorbed by space. The more space expands, the more the photon's energy is depleted. This explanation sounds reasonable, but is actually not entirely accurate. From the perspective of a photon, it doesn't lose energy while traveling through space. Photons only appear to lose energy in our measurements. This may seem contradictory because our measurements are not wrong, yet the photons themselves remain unchanged. This is a clear example of the relativity of the universe. Depending on the reference frame you are in, your perception of reality changes. While only one reality is unfolding, the reference frame determines what you observe. So, after all, the question of whether photons exist forever in time has an answer. The truth is, photons do not disappear. They will continue to exist, even if the universe ends in heat death. Time will keep passing, space will keep expanding, and photons will remain unchanged. Photons always exist because their energy is never lost. They just gradually fade from our perception. Finally, we can summarize the key points from this section. First, in terms of particle physics, we can confirm that photons are eternally stable particles. As long as they do not interact with matter, photons will not decay into any other particles and can travel through space indefinitely. Second, the cause of redshift has nothing to do with the photons themselves, because photons do not lose energy. The real cause lies in our reference frame. Earth, the solar system, and even the Milky Way are all moving. Combined with the universe's expansion, this results in the photon's energy appearing to change in our measurements over time. The final consequence is that the universe is gradually dimming in our view. This is a reality we must accept, even though it might only be true within our reference frame. But we don't need to worry too much. This process of the universe becoming completely dark and invisible will not happen anytime soon. It will occur slowly over an infinite span of time, meaning as time passes, the universe will fade from view with each observation. All of these processes require an infinite amount of time to complete. And whenever infinity is added to the equation, everything becomes extremely ambiguous. A star's equilibrium is maintained by a balance between the energy generated by nuclear reactions in its core and the inward pull of gravity. When a massive star dies, it undergoes a supernova explosion. At some point, the outward pressure must overcome gravity, right? If so, when does this happen? First, it's important to note that there's no known natural event that can match the raw energy released by a supernova in a single moment. If the speed of light were instantaneous, supernova would be visible across the entire universe. Despite decades of study, astronomers are still unsure about the exact mechanism that triggers a supernova. Even the most sophisticated computer simulations haven't fully resolved this puzzle. Some studies have presented us with rather surprising answers. For instance, the sound waves emanating from the star's core could be the trigger for the explosion. In white dwarfs, the explosion is caused by gravity reigniting nuclear fusion. For most of a star's life, if not its entire existence, from birth until just before the explosion, outward pressure dominates gravity. Although we all know the ultimate outcome, gravity will eventually win, it's clear that during the battle, outward pressure is the stronger force. So, when the battle ends and gravity wins, why does the star explode instead of simply collapsing? Clearly, while some material collapses inward, other material is ejected outward. Most scientific papers provide a rather general overview of this event. A closer look reveals that a supernova is actually a sequence of events, not a single occurrence. This sequence typically unfolds over a few seconds, or even a fraction of a second. The key point is that telescopes can only observe the final event when the star explodes and emits light, while all the preceding events remain hidden. For a star that is 8 times or more massive than the Sun, its core becomes increasingly heavy and hot, until nuclear reactions produce iron. When the star's metallic core contracts to a size comparable to Earth, but with a mass 1.5 times greater than the Sun, the core's density is so extreme that it forces electrons and protons to merge, forming neutrons. This process releases a tremendous number of neutrinos and energy. However, it also eliminates the electromagnetic force within the atom, as neutrons have no charge. As a result, the star's core rapidly loses support, leading to a sudden drop in pressure. Gravity then takes over. Within half a second or less, the Earth-sized metallic core collapses to a diameter of just over 20 kilometers. In scientific terms, this is known as core collapse or implosion. Immediately following this collapse, the core solidifies, creating a sound wave with a frequency of about 300 Hz that propagates outward. The shock of the collapse rebounds, driven by the strong nuclear force. Simultaneously, more neutrinos and heat are released. After the core collapses, it creates a large void, drawing the outer layers inward. But because the core has become incredibly dense and hot, it cannot interact with the outer layers. For a brief moment, around 200 milliseconds, the entire star becomes quiescent in a shock stall. This is enough time for sound waves to probe the weakest points in the star's outer layers. And then, a supernova erupts, ejecting 60 to 70% of the star's mass. The only remnant is an extremely dense object known as a neutron star. Therefore, we can conclude that a supernova is a sequence of events, not simply a single explosive outburst. Moreover, each star will produce unique variations in this process, which we can explore in another video. How do astronomers know if a planet, especially a distant one, harbors life? And how can they determine a planet's composition and atmospheric makeup from such a great distance? First, it's important to emphasize that we don't definitively know if any exoplanet harbors life. All of the super-Earths we've found so far are merely potential candidates, not confirmed abodes of life. Numerous factors influence the habitability assessment of a planet, including the luminosity of its host star, its orbital distance, and the amount of starlight it receives, its estimated composition and mass, as well as its atmospheric composition. The issue is, how can we know the atmospheric composition of that planet? We know that the most abundant elements in the universe are hydrogen and helium, so a planet's primordial atmosphere would certainly contain these gases, along with some simple compounds like methane and ammonia. For planets far from their host star, they are primarily made of gas, with a relatively small core. Over time, their atmospheric composition seems to remain unchanged. On the other hand, rocky planets with solid surfaces like Earth tend to have atmospheres that change significantly due to volcanic activity over billions of years. Additionally, to understand the detailed composition of a planet's atmosphere, scientists can use spectral analysis. For planets that are too distant, telescopes cannot gather enough data for analysis. In such cases, scientists consider other factors like mass, size, age, distance from the star, potential heat received, and mass loss over time, etc. These pieces of information are then matched with predefined models, such as comparing them to our solar system. In general, this information cannot provide a 100% accurate result, and we all understand that these relative estimates are the most reliable conclusions science can offer. Why is the universe older than 13 billion years, but has a diameter of more than 93 billion light-years? And how can we see light from the edge of the universe? To determine how vast the universe is, we have many different methods of calculation and estimation. But if we want the most accurate measurement possible, we must use ultra-sensitive, specialized machines. The Wilkinson Microwave Anisotropy Probe, WMAP, is one such device. It measured the farthest and oldest light wavelengths of the universe that its sensors could detect. As light travels farther distances, its wavelength shifts towards the red end of the spectrum, a phenomenon known as redshift. After careful calculations, the oldest photons that the probe can observe are located approximately 46.5 billion light-years away from Earth. Therefore, the diameter of the universe is at least 93 billion light-years. These faint photons are the cosmic microwave background radiation, the farthest reaches of the observable universe. The universe may be even larger, but 46 billion light-years is currently the farthest distance that human technology can measure. Is it feasible to create oxygen on Mars? If Mars had a strong enough magnetic field, would releasing oxygen create an ozone layer like Earth's? Mars is considered to have little geological activity, so what would its magnetic field be like? If we use nuclear bombs, as Elon Musk suggested, would that be feasible? Clearly, terraforming Mars into a second Earth is not a simple task, considering both scientific logic and practical realities. No matter how optimistic we are, we must acknowledge that there will never be two Earths in the solar system. Even if we find another extremely ideal planet in the future, Earth will always remain a paradise for life. Returning to the question, is it feasible to create oxygen on Mars? The answer is no. If we were to overcome all the challenges and create oxygen on Mars, things would gradually improve. Oxygen, being a heavy atom, would easily settle on the planet's surface without being blown away by solar winds in a short period. The presence of oxygen in the atmosphere would also naturally lead to the formation of an ozone layer. Ozone, with the chemical formula O3, is formed by the interaction of ultraviolet radiation with O2. Ultraviolet radiation is a component of sunlight with a wavelength ranging from 200 to 315 nanometers. When ultraviolet radiation interacts with O2, it splits O2 into two single oxygen atoms. Each single oxygen atom can easily combine with another O2 pair to form O3, or ozone. Once formed, ozone continues to interact with ultraviolet radiation, splitting back into O2 and a single oxygen atom. Thus, the formation of ozone in the atmosphere is a cyclical process. Therefore, if the atmosphere of any planet contains oxygen, it will certainly form an ozone layer, although the thickness may vary. What about Mars's magnetic field? If we were to use nuclear bombs to terraform Mars, as Elon Musk has suggested, would that be feasible? After decades of research, we know that Mars's magnetic field is very weak. This is likely due to its core cooling and solidifying. Detonating nuclear bombs on Mars might temporarily reactivate some geological activity. However, that's not Elon Musk's primary goal. He envisions detonating bombs at Mars's poles to release trapped ice, water, and CO2, triggering a greenhouse effect to warm the planet. While this idea sounds logical and exciting, the reality is more complex. Recent studies show that the amount of CO2 trapped beneath Mars's surface isn't enough to create a significant greenhouse effect. In fact, it could make Mars even colder, as the resulting dust clouds would block out what little sunlight reaches the planet. These dust clouds could take decades or even centuries to settle, which doesn't align with our goal of landing on Mars in the next decade. Furthermore, acquiring the necessary funds and bombs for such a mission is impractical. It's estimated that 10,000 nuclear bombs would be needed to significantly alter Mars, while the global nuclear stockpile is around 13,000, with 90% belonging to Russia and the United States. The cost of producing a single nuclear bomb ranges from $20 to $50 million, and a rocket capable of delivering it to Mars costs between $200 and $250 million. Even if the funds were available, no country would likely provide Elon Musk with nuclear weapons. Additionally, producing nuclear weapons is against international law. Clearly, nuking Mars is not a viable option. In the universe, what forms does matter exist in? Does the Bose-Einstein condensate exist outside the universe? And what are its properties? If we were to list them all, there are actually 7 different states of matter in the universe. However, humans have only observed 5 of them: solid, liquid, gas, plasma, and Bose-Einstein condensate. We are already familiar with solids, liquids, and gases, so I won't go into detail about those. Plasma is a high-energy state of matter. While it's relatively rare on Earth, it's likely the most common state of matter in the universe, as seen in our Sun. Under extreme heat and pressure, atoms become highly energized and behave chaotically, forming a charged ionized soup. It's like a superheated, electrically charged fluid that's both solid-like and fluid-like. Bose-Einstein condensate, BEC, was first created by scientists in 1995. It's essentially the opposite of plasma. To achieve this state, matter must be cooled to near absolute zero. At such extremely low temperatures, atomic motion virtually ceases, and there's minimal energy transfer between atoms. Individual atoms begin to coalesce, behaving as if they were a single entity. Light passing through a BEC is slowed down, allowing scientists to more easily study the principles of waves and particles. Theoretically, this state can naturally occur in the universe because the cosmic background temperature is already very cold, only 2.7 Kelvin above absolute zero. Bose-Einstein condensates have also been used to simulate conditions that might exist within black holes, as black holes can be even colder than the cosmic background. The remaining two states are neutron degeneracy and quark-gluon plasma. These states only exist under extremely harsh conditions, such as in the core of a neutron star. Therefore, these two states are still only hypothetical. Why are galaxies moving away from each other, yet the Milky Way and Andromeda galaxies are merging? This is definitely a question that many of you have. The universe is expanding, and scientists always say that galaxies are moving away from us. But when galaxies are bound by gravitational force, they cannot move away further. It's simple, like our solar system. It always maintains its motion, because the planets are bound by the sun's gravitational field. The heavier the object, the stronger the gravitational force. But the farther the distance, the weaker the gravitational force. Are all planets on the same plane? I can't give you a definitive yes or no. While the protoplanetary disk from which our solar system formed was essentially flat, which would suggest that planetary orbits should align. Subsequent collisions, impacts, and disturbances have likely disrupted this initial alignment. If we imagine the universe as a 2D plane, the sun's gravity would create a dent in that plane, and all the planets would orbit within this dent. However, the four-dimensional universe is far more complex and challenging to visualize. Things may seem chaotic, but there's an underlying order. We're essentially moving very stably within this apparent chaos. Imagine a spaceship launched from Earth, traveling at a constant speed of 10 kilometers per second. Could it escape the Earth's gravity? The answer is yes. Regarding the first cosmic velocity, this is the speed an object needs to achieve in order to orbit a planet. For Earth, this speed is approximately 7.9 kilometers per second. To completely escape Earth's gravity, an object must reach a speed of 11.2 kilometers per second. For instance, a rocket launched from Earth cannot immediately attain the necessary speed to escape the planet. Instead, it orbits Earth multiple times to gain speed before finally breaking free. As the rocket ascends, the atmosphere becomes thinner, reducing air resistance and making acceleration easier. Therefore, while speed is a sufficient condition, energy is the necessary condition. Imagine climbing a hill in a car that always goes 10 kilometers per hour. Right after reaching the halfway point, it slows down and stops at a certain distance, unable to go any further. But if 10 kilometers per hour is a constant speed, regardless of resistance, it should definitely be able to climb the hill at that speed. Similarly, for a spacecraft, if you maintain a constant speed of 10 kilometers per second without running out of fuel, you should definitely be able to escape Earth's gravity. The main issue here is energy. When virtual particle pairs are created near the event horizon of a black hole, if one particle accidentally falls into the black hole, to conserve energy, the particle that falls in must have negative energy. So why can't it be the opposite? The particle that falls in has positive energy, and the particle outside has negative energy. When a pair of virtual particles is created in empty space, it consists of one negatively charged particle and one positively charged particle. After interacting, the two particles annihilate each other, leaving no trace or excess energy. However, if particle pairs are created near the event horizon of a black hole, and one particle inadvertently falls into the black hole while the other does not, the virtual particles cannot interact to annihilate each other. As a result, the virtual particle outside suddenly becomes a real particle, as it transitions from a virtual state to a real one, from nothing to something. Therefore, the particle that falls into the black hole must have negative energy. When the negative energy particle is pulled into the black hole, it interacts with another particle inside, causing the black hole to lose a particle. In this case, a particle is spontaneously created outside the universe, and the black hole must lose a particle to conserve energy. It's as if the particle has somehow escaped the black hole. What is meant by physical information that is always conserved in a black hole? For example, if a black hole swallows a star, how can it emit Hawking radiation and still retain the star's information? You might be wondering why Stephen Hawking, a brilliant mind behind black holes, never got a Nobel Prize. Well, it's because his ideas were so out there that scientists haven't been able to prove them just yet. We have never observed Hawking radiation in reality, although many scientists believe it is plausible. When a star falls into a black hole, it simply disappears or remains stationary inside the black hole. All information about the star, such as brightness, temperature, electric field, or metal composition, etc., is converted into mass and a little angular momentum. In this case, mass is a form of remaining physical information. It tells us one thing: everything in the universe is described by some form of information. Objects do not simply disappear, but are only transformed from one form to another, or from one place to another. Black holes swallow everything and release nothing. Therefore, any physical information that falls into a black hole is permanently trapped. Returning to Hawking radiation, the theoretical physicist Stephen Hawking proposed that black holes gradually lose mass by emitting this radiation. However, this radiation doesn't carry any information about what has fallen in. This raises a perplexing question. If black holes eventually evaporate, where does all that information go? Over the past few decades, there have been numerous attempts to resolve the black hole information paradox. Theories ranging from general relativity to quantum mechanics have been proposed, but it's clear that this is not a problem that will be easily solved. In essence, based on our current understanding, there's no known way to recover the original state of an object once it has fallen into a black hole. This has led many to speculate that black holes might be portals to other universes. In summary, the universe is a place filled with mysteries and unanswered questions. From vacuum decay and the nature of matter to the enigmas of black holes and theories about the universe's future, there is an abundance of fascinating topics waiting to be explored. We've only just begun our journey to understand these cosmic phenomena, and with each step we take, new questions arise. Our exploration of the universe will continue to take us on amazing journeys as we seek to understand space, time, and the unknown. That's what Nothingverse is all about, bringing you the latest in science and space exploration. If you have any questions about the universe, astronomical phenomena, or any other scientific topic, feel free to leave a comment below. I'm excited to answer your questions in future videos.